So lab 1, verification of KVL and KCL. So we will be verifying Kirchhoff's voltage law and Kirchhoff's current law in this experiment. For this experiment, for this lab, we will perform two experiments, one for the verification of KVL and another for the verification of KCL. So as we know that in series circuit the voltage drops differ and the current remains the same, so we will use a series circuit to verify KVL, and for KCL we know that in parallel circuits the voltage across the parallel branches remain the same, but the current differs for each of these branches. So we will verify KCL using a parallel circuit, more specifically a series parallel circuit. So first we will be performing experiment 1, verification of KVL. For this experiment we will need one 5K resistor, one 10K resistor, one 15K resistor. We will also be needing one breadboard, which is located here, a function generator, and a digital storage oscilloscope, some wires, and a DMM. So let's move on to the circuit. You see, in this circuit we will need a 4-volt peak 2 kHz source, and there will be three resistances R1, R2 and R3 connected in series to the source. For series connection, notice that each component has two different nodes in each of its legs. That is, for R1, one leg is connected to node A, another node is connected to node B. For R2, one leg is connected to node B, another leg is connected to node C. And for R3, one leg is connected to node C and another leg is connected to node 0. So two legs are in two different nodes. For a series circuit, there is always one common node and one different node. That is, two legs will be connected to two different nodes. So for this circuit we have this data table, lab 1 experiment 1. So before building the circuit we need to measure the practical values of the resistance that we will use, and we will record them in this data table. So I have collected the resistances. Now I'll attach them to the breadboard to take the practical values of these resistances. As you see, I have connected the resistances separately in three different locations so that I can measure the practical value of the resistance. Now I'll use the DMM to measure these values, and I'll record the corresponding values in the data table. So to measure the practical values of the resistances, I need to put the DMM in resistance measurement mode, and then I connect my probes to the resistances. So this here is 9.99 kilo ohm. So this one is the practical value of R2, our 10K resistance. So I'll record the measured value here, 9.99 kilo ohms. The next resistance, this is 14.76 kilo ohm, which is our R3 15K resistor. The practical value is 14.76 kilo ohms. The last resistor, it's 4.91 kilo ohm. So this is R1 kilo ohm. So now we are ready to build our circuit. So first we take the 5K resistor and attach it. I connect one leg to a node and another leg to a different node. So referring to the circuit, I connect one leg at A, another leg at B. So if you see at the circuit, this is A, this is B, A, B. At B, I will connect one end of the 10K resistor and another end to a different node. So I attach one leg of 10K to B, node B, and another leg to node C. So now this is node C. Going back to our circuit, we'll attach one leg of 15K to C and another leg to a new node 0. So I attach one leg of 15K at C and another at a separate node 0. Now we have connected the resistances in series. Now we'll need to connect the source, and we'll use the function generator as the source. So this is the probe of the function generator. This is the probe of the function generator. This is the red wire, the plus polarity, the black wire, the negative polarity. So according to the circuit, we will attach the red wire, the plus polarity, to node A, and black wire, negative polarity, to node 0. So the red wire will go to this node A, and the black wire will be attached to this node 0. Before I can attach the wire, I have to connect connecting wires to these clips. So I open the clips and place a connecting wire. Be warned, don't wrap wires around like this. This can cause breakage, and it will harm your readings and experiments. Same for the black clip. I open the clip and place a wire. Okay, so now our wires are ready for connecting. I connect the red wire to node A, and the black wire to node 0. Our circuit is now complete. We have completed the circuit according to our circuit diagram. So this is our completed circuit. Now we'll need to attach oscilloscope for taking the different readings. So this is the oscilloscope with channels. This is channel 2, this is channel 1, and this is channel 2. So the two probes of the oscilloscope, channel 1 and channel 2. So just as we did for our function generator, we'll have to attach connecting wires with our probes, which I will do now. I open this clip and attach an wire, and I open this part by pressing down and attach the wire. I will prepare the other channel similarly. I press down the clip and place a wire. I press down this part, expose the connecting region, place a wire, and lock it. So both of our channels are now ready for use. So in the circuit, first we have to calibrate this source to 2 kHz and 4 volt peak and for that we need a channel at node A. So I will connect channel 1 to node A. The black wire always goes to the ground, and the positive part is connected to the node you need. So I'll connect this to node A, which is here, as explained previously. As you see from the circuit that we have to take readings of R1, R2 and R3. To do that, what we have to do is we have to take voltage readings of the appropriate nodes and then measure the appropriate voltages. Since R3 is connected between C and ground, we can directly get the voltage at node C from channel 2 if we attach it at C, and for R1, if we attach channel 2 at node B, we will be able to get the voltage across R1 by subtracting VB from VA. So VA minus VB. So if channel 1 is connected at A and channel 2 is connected at B, we will use the math function of the oscilloscope to perform channel 1 minus channel 2 to get the voltage across the resistance. And as for the R2, it's between node B and node C. We will have to place one channel at node B, one channel at node C, and then we will have to perform VB minus VC. So if I place channel 1 at B and channel 2 at C, then it will be channel 1 minus channel 2. That's how we will take the readings for the oscilloscope. First, we will measure VR1. To measure VR1, we will need to connect one channel at A and one at B. Already channel 1 is placed at A, so we will need to place channel 2 at B. I place the black wire in the ground and the positive part at this node B. So we are ready. Now we have to move to our function generator and oscilloscope for the next part of the experiment. We will have to set 2 kHz 4 volt peak for this experiment. So I turn on the function generator by pressing the power button. I turn on the oscilloscope by pressing the power button on the top. By default, the function generator is giving triangular output. We have to change it to sinusoidal by pressing this sinusoidal button. The output is 2 kHz. We have to increase it to 4 kHz. I do that by increasing the frequency knob. So it's 4 kHz. To set the amplitude, we will have to move on to the oscilloscope. So the oscilloscope is in a default setting that is stored from previous use. To set the oscilloscope properly for use, what you can do is press default setup and then adjust accordingly. So by pressing default setup, we are getting this output. So to make the waveform visible, I decrease the time per division by rotating this horizontal knob to make the cycles appear clearly. Then I can rotate this vertical knob for channel 1, which is shown in yellow, and increase the volts per division so that my graph is displayed in the screen properly. Channel 2 is turned off. I press channel 2 and channel 2 is displayed. I reduce the volts per division to 2, and now both of the signals in channel 1 and channel 2 are displayed properly. Notice that when I press channel 2, a menu appeared where coupling is DC. This should be changed to AC for all experiments in EEE 241L. So how you can change it is press the channel button, channel 1 or channel 2, If I press channel 1, I'll get this menu. For coupling, which is fixed to this button, press once and it will become AC. Now move on to channel 2, press the channel 2 button, coupling is DC, press this button once to get to AC coupling. Once you set the coupling, you should press the position button to ensure that your signals are located at the axis symmetrically. Now you can turn off this menu by pressing this menu on off button. Now both of our signals are displayed. In measure, we see that channel 1 voltage peak to peak is being displayed here, channel 1 Vmax is being displayed here, channel 1 V minimum is being displayed here, and so on. We can change this according to our need. Let's retain the channel 1 settings and set channel 2 settings in these boxes. So I will set channel 2 voltage peak to peak in this box. Then voltage source will be channel 2. I press this button. The type is V minimum. I press the corresponding button to get this menu. I rotate this universal knob to get V peak to peak. Then I press return. So now channel 2 V peak to peak is being displayed here. Now I will change this to channel 2 Vmax. I do that by pressing this button. Category is again voltage, channel 2. Type will be Vmax. So I press this once and see that Vmax is already selected, so I don't need to manipulate anymore. So I press return and see that channel 1 V peak to peak, channel 1 Vmax, channel 2 V peak to peak, and channel 2 Vmax is displayed here. So our first task is to adjust our source. We have already set the frequency to 4 kHz. Now we need to set the amplitude to 4 volt peak. So 4 volt peak is the amplitude of our source. So 4 volt peak. So we need 4 volt max. So we have connected channel 1 to node A, which is the source. So we'll increase or decrease the amplitude until we get 4 volt peak, that is 4 volt max over here. So it's 4.40 volt, very close to 4 volt. I'll decrease the amplitude a bit to get to 4 volt. So we have set 4 volt max. Now we are ready to take the readings since our source has been set and our circuit is ready. So for taking the reading of resistance R1, we connected channel 2 to node B, and the voltage of the voltage across the resistance R1 would be displayed if I subtract channel 1 and channel 2. Channel 1 minus channel 2 will give me the signal for the resistance. I can do that by pressing the math button here. See that source is A is channel 1, source B is channel 2, which is what we need. So operation is seen to be plus, this should be minus. I do that by pressing this button. So minus is now displayed. So channel 1 minus channel 2. So this new signal, this purple signal, is the resistance across R1. And to measure the voltage across this curve, we will need cursor. So I turn on the cursor by pressing this button and changing the mode to manual. The source should be math, as I am measuring the signal produced by the math function. The type would be voltage, as I am going to take the reading for the peak to peak voltage. You see here that in our table we have the required reading for both peak to peak and peak voltage. So we can record either, as this oscilloscope provides us the option to produce either. So If I record Vmax, I can calculate V peak to peak by multiplying by 2, or if I record peak to peak, I can get peak voltage by dividing by 2. So I'll record peak voltage Vm or Vmax. So using the cursor to get the peak to peak voltage, I'll have to take cursor B to 0 and cursor A to the peak of the purple signal. So I select cursor B by pressing this button, and if I rotate the knob, you'll see that the value of cursor B is increasing and 0. So I've reached 0. Now if I take cursor A to the peak of this purple curve, I'll get the voltage of the resistance. So I'll select cursor A and take the cursor to the peak. So it's 560 millivolt, and this should be recorded in our table. So VR1 is 560 millivolt peak. So I record that here. Now if I move on to our next reading R2, you see that we have to connect one channel at node B and another channel at node C. So we have already channel 2 connected at node B. So what I can do is I can move channel 1 from A to C, which I am going to do now. So I take channel 1 from node A and reconnect it to node C. So now we have taken our oscilloscope, connected our oscilloscope to the required region, and from the circuit diagram we see that voltage of R2 is VB minus VC, which would be channel 2 minus channel 1. So in the oscilloscope, we go to the math feature. Previously the setting was channel 1 for source A, channel 2 for source B. So the calculation was channel A, source A minus source B, that is channel 1 minus channel 2. But since the configuration of our oscilloscope connection has changed, we have to perform channel 2 minus channel 1. So we have to change source A from channel 1 to channel 2 by pressing this button, and source B to channel 1 by pressing this button. Now we are getting our required signal in the shown by the purple signal. And as previous, we'll go to the cursor menu. We see that cursor B is already at 0 volt. We'll have to take cursor A to the peak of this curve. So cursor A is already selected. I rotate it to go to the peak. It's 1.44 volt shown in del V. So 1.44 volt for VR2, and I record that in this table. Next, for VR3, I just have to have a channel present at node C. So we already have channel 1 located at node C. So the voltage of peak voltage of channel 1 is our voltage drop across R3. So in our oscilloscope, is if we go to the measure window, the channel 1 Vmax is the peak voltage drop across resistance R3, which is 2 volt, and we can record it directly in our table. So we can write 2 volt for VR3. So we have completed our calculation using oscilloscope. Now we have to measure the same values using DMM, which we are going to do now. DMM always gives result in RMS for AC signals, so we will be filling up this table using our DMM, and then we can calculate the peak voltage using this formula shown here. Since we have completed our recording using the oscilloscope, we can remove the oscilloscope channels. Carefully, and then we can attach the DMM and take the required readings. So first of all, ensure that the black probe of the DMM is connected to the COM section and the red is connected to the this location where it's labeled capacitor voltage ohm and hertz here. So this is the appropriate location for voltage measurement. And now we will have to take our knob to the voltage reading section here. By default, the DMM will take DC readings as indicated here. To go to the AC reading, we'll have to see the symbol. You see that there is a sinusoidal symbol in blue. That means to reach AC voltage measurement, you have to press this blue button. Press this. Now see, the reading will be now in AC as indicated by this AC symbol in the display. So first we'll measure the RMS voltage of the source Vs by parallelly attaching our probes to node A and node 0. It is being displayed 2.545 volt RMS. We record that here, 2.545 volt RMS. Then we take reading for VR1. We place the DMM, attach the probes parallelly to R1. Two probes in two legs. 0.416 volt. Then for resistance 2, 0.851 volt RMS. And for resistance 3, 1.260. So we have completed taking readings for these three resistances using the oscilloscope and the DMM. We can calculate the rest of the readings easily through mathematics. Also note that the frequency is the same for all, which is 4 kilohertz as indicated in our circuit diagram. Sorry, here. Okay, so we have completed our experiment on verification of KVL. Okay, so now we move on to our next experiment, verification of KCL. We will be using this circuit to verify this KCL. As you see, we are using the same resistances from the previous experiment verification of KVL, 5K, 10K and 15K. So first what we should do is we can record the same measured values in this table as for the verification of KVL. So we can take the previous readings. So we can take the previous readings and record the same values for the measured values, since we are using the same resistances. So this is 4.99 kilo ohm, this is 9.99 kilo ohms, and this is 14.76 kilo ohms. So we have measured we have recorded the practical values of the resistors. Now we move on to our circuit. So now we see that this is R1 5 kilo ohm, this is R2 10 kilo ohm, and this is R3 15 kilo ohm. Our previous circuit was connected like this. This is R1, R2, and this is R3. So if you notice, if we just remove this R3 and place it in parallel to R1 and R2, we will get to our desired circuit configuration: R1, R2, and R3. So R1, R2, and we have to attach R3 in parallel to R2. So this is R1, R2, and R3. We have completed our circuit. As per the circuit diagram, node A, node B, and node 0. So this is node A, this is node B, this is node 0. Now we need to connect the source. To connect the source, we connect the signal generator. The signal generator, the plus polarity or the red wire will be connected to A, the minus polarity or the black wire will be connected to 0. So the red wire is connected to A and the black wire is connected to 0. So we have connected the source. So now we see that here the source is 5 volt RMS 10 kilohertz. So what we can do is we can use the DMM to set the source, and also we can use the oscilloscope to set the source voltage. For this this time we will be using the DMM to set the source. So I turn on the function generator by pressing this button, and the frequency is 10 kilohertz, so I increase to 10. I have reached the max, I cannot get to 10, so I decrease the knob, change the range, and go to 10. So the probes are connected in the proper channels. I move the knob to the voltage measurement mode and press the blue button to get to AC measurement. Now I hold the probes between node A and node 0. So we see that the voltage is 1.56 volt. This should be set to 5 volt, and I keep increasing the amplitude to get to 5. By default, our signal generator is triangular. We change it to sinusoidal. Then we adjust the amplitude. To 5 volt RMS. It's currently 2.8. I increase the amplitude. So 5 volt RMS has been set. We can also measure the frequency by taking the knob to this hertz position and placing the now placing the probes in parallel to the source is 10.18 kilohertz. So very good. So I turn off the DMM for now. Now referring to our data sheet, first we have to measure currents, source current IS, that is IR1, IR2 and IR3 using the DMM, and then we will have to use the oscilloscope to find the current. We already know that oscilloscope cannot measure current directly, so we will have to use indirect method of voltage calculation and division by resistances to find the current when using oscilloscope. So first let's measure the currents using DMM. So to get an idea of how to connect the DMM, to get the source current IR1, we have to connect the DMM in series in this location or in this location. For getting current of R2, we have to connect the DMM in series with R2 in this location or this location, same with R3, here or here, series DMM. So for current measurement, we have to change this probe. We have to disconnect it from here and connect it in this location for current measurement. Then we have to take this knob to this milliampere, microampere range, whichever one is suitable for us. So I am taking it to the milliamp region. See, it's set for DC measurement. I press the blue button to get to the AC mode. Now I can measure AC current. Always the DMM should be connected in series for AC, for current measurement. For any current measurement, DMM should be in series. So first I measure R1 by placing the DMM in series with this connection. To make the series connection, I have to move the wire and place the DMM in series like this. As you see, the recorded current is 0.48 milliampere, which should be recorded in the table. 0.48 milliampere for the source. .48 milliampere for IR1. Now we place the wire back to its original position. Now we have to place the for measuring IR2, we have to place the DMM in series with R2, which is located here. So to do that, I remove one leg of R2 and attach it at a separate node, and then connect the DMM. You see that 0.25 milliampere is the current which we will record here. 0.25 milliampere. Then we place the resistance back to its original node B. Same thing for current R3. We remove one leg of R3, place it in a different node, and then attach the DMM in series. It's 0.15 milliampere. 0.14 milliampere for IR3. So we have recorded the currents using DMA. We place back our resistance in its original position. Turn off the DMM and place the red probe back to its original position. Now, according to the data sheet, we have to record the voltages across R1, R2 and R3 using the oscilloscope. Here it's written peak to peak voltage, so we'll be recording peak to peak voltage here. So I turn on the oscilloscope by pressing the power button over here. From the circuit diagram, we see that the voltage across R1 will be VA minus VB. So for recording R1, we have to place one channel at node A, one channel at node B. So I will connect channel 1 to node A. Black wire always goes to the ground, and this part goes to node A. For channel 2, I'll connect it at node B. So this black wire is always connected to the ground, and this end goes to node B. Now we'll go to our oscilloscope. Here we see channel 1 V average. We have to change it to channel 1 V peak to peak. Okay, we can set channel 1 V peak to peak here by pressing this button, going to voltage and taking this to voltage peak to peak, which is currently 18 volt. Okay, so I decrease the volt per division, and then increase the time per division a bit. Okay. So since channel 1 is connected to node A, channel 2 is connected to node B, the voltage of R1 is channel 1 minus channel 2, which we will do by pressing math. Source A will be channel 1, source B will be channel 2, operation is minus. So this purple wave, this is the voltage across the resistance. To measure the peak to peak voltage, we'll go to cursor. The mode is manual. Cursor B should be at the negative peak of the curve, and cursor A should be at the positive peak of the curve. Here, this del V, this is the peak to peak voltage of R1. It's 9 volt, and this should be recorded at the table. So peak to peak voltage of R1 is 9 volt. Since R2 and R3 are parallel, their voltage will be same, and their voltage can be found by finding voltage of node B, VB, and we know channel 2 is connected to node B, so channel 2 V peak to peak will give us the peak to peak voltage across R2 and R3. So we can find that by pressing measure. Channel 2 V peak to peak is noted here, 10 volts. So for both of this, it will be 10 volt. So we record this value in our tape. it's around 10.4 volt. So 10.4 volt, 10.4 volt. From these voltages we have to calculate the corresponding RMS current, and it will then be prepared for comparing with our current calculations here. So for this experiment we have completed taking all the readings required from the equipments.